Welcome back. As we've seen, the relationship between two quantitative variables can sometimes be modeled well by a straight line, and the linear relationship can be strong or weak depending on how much of the variability that the regression line explains. In this video, we'll look at answering the question, but is the relationship statistically significant? We'll start with this example. Our anthropologist is interested in how accurately she can predict age at death from human skeletal remains. She examined 400 skeletons and estimated the age at death for each skeleton. Our variable of primary interest is the difference between the estimated age and the actual age at time of death. We'll call this the error in age estimation. There are many possible factors that might affect the error in age estimation. In this video, we'll consider how it is related to body mass index, or BMI. It may be that deterioration of bones varies with BMI, and as a result, age estimates based on bones may be more or less accurate depending on BMI. We'll be using the numerical measure of BMI here. Before investigating the relationship between BMI and error in age estimation, we need to decide if one of these variables is playing the role of response variable and the other the role of predictor variable. Since we are interested in learning how BMI affects the error in age estimation, it's clear that BMI is our predictor and error in age estimation is our response. Now let's look at a scatter plot of error in age estimation and BMI. This scatter plot is pretty noisy, and it's not clear if there is a relationship. But if we use the method of least squares to estimate the equation of the line that might describe this relationship, if there is one, we get that the estimated error in age estimation is 23.28 plus 0.41 times the BMI. For this regression line, R squared is 0.019, so only 1.9% of the variation in the response variable is being explained by its linear relationship with the predictor, BMI. So is there really a relationship between error in age estimation and BMI? Or could the fact that we got a positive slope here just be due to chance? We can answer this question by carrying out inference for the slope of the regression line. Let's review the process of statistical inference. In the real world, we have some observed data. And in the theoretical world, we have some models, statistical and scientific, which may be useful in describing the real world. In regression, our model is the straight line model, used to describe the relationship between the response and the predictor variable. One of the features of all statistical models is the variation that we naturally have in our observed data. All of our data won't lie perfectly on the straight line. The data will be randomly scattered about it. To account for this noise in our model, we add an error term to the equation of the straight line. So our model is y, our response, is beta 0 plus beta 1 times x plus epsilon. This model uses two Greek letters, beta and epsilon. Beta 0 is a parameter. It is the theoretical world value of the intercept. Similarly, beta 1 is our slope parameter. We can never observe these parameters, but we can get estimates for them from our data. We've already seen how to estimate the intercept and the slope using the method of least squares, and we call the resulting estimates B0 and B1. Epsilon is our random error, giving how much each point differs from the line in the vertical direction. Graphically, we can illustrate our model like this. Our model says that y and x are related by a linear relationship. Our data points are randomly scattered about that line, with that random scatter captured by the epsilon in the model. We typically model the random scatter of the epsilons as having a normal distribution. So for a given value of x, we get a distribution of values of y centered on the linear model with a bell shape, and we'll assume we have the same standard deviation regardless of the value of x. We estimate the betas from our data, and that gives us the b's, and we'd like to infer what we can about what the betas really are from what we've observed. The usual question in regression is beta 1 equal to 0? If it is, our model is a horizontal line, and the line gives the same value of y for every value of x. Then we'd say that there is no linear relationship between y and x. If our goal was to understand if x and y were linearly related, we'd say they weren't. And if our goal was to use x to predict y, we'd say it's not a good predictor of y. So we're interested in making inferences about the slope, that is, the parameter in the theoretical world model beta 1. And we're especially interested if it is 0. Our inferences will be based on our observed value of beta 1, which is b1. b1 is a statistic as it is calculated from our data. For every sample of data we might observe, we'd get a slightly different value of this statistic. And all the different values it could be in all possible samples has a distribution, which is the sampling distribution of the estimate b1. Our theoretical world model assumed that our data were scattered about a line with the scatter determined by a probability distribution, which we assumed to be normal. And if the errors are normally distributed, then our observed values of the response variables and the estimators calculated from them are also normally distributed. For every normal distribution, we need its mean and its standard deviation. b1 is an unbiased estimator of beta 1, so the mean of its sampling distribution is beta 1. For its standard deviation, we'll estimate it from the data. We won't go into how it is estimated here. We'll leave that for a later course and trust the values we get from statistical software. The estimate of the standard deviation of the sampling distribution of b1 is called its standard error, which we'll denote as SE for standard error of b1. Now we can carry out a statistical test for whether the slope parameter is 0. And if it is, we have evidence that there is actually no linear relationship between our x and our y. The hypotheses we'll test are the null hypothesis that there is no relationship, so beta 1 is then 0, versus the alternative that there is a relationship, so beta 1 is then something other than 0, for a two-sided alternative. We've seen other statistical tests where the sampling distribution of the estimator is based on the normal distribution. For example, our test for the mean. For this test, the test statistic was constructed as the estimate of the mean, standardized by subtracting its assumed value under the null hypothesis, and then dividing by the standard error of the mean. For our regression test of the slope, the null hypothesis value is that beta 1 is 0, and our test statistic becomes our estimate of the slope divided by its standard error. Once we have our value of the test statistic, we calculate our p-value, the probability of observing the value of the test statistic we got, or a value more extreme, assuming that the null hypothesis is true. The test statistic has a t-distribution instead of normal, since we estimated the standard deviation of b1 by its standard error, that is, the value we estimate using our data. And in regression, the t-distribution has n minus 2 degrees of freedom. N is the number of data values we have, and we lose 2 degrees of freedom because we had to estimate two parameters, the slope and the intercept. Now back to our skeletons. We're looking at the relationship between error in age estimation and BMI. We're not sure if this observed linear relationship is just due to chance, so we'll carry out a test of whether the slope is 0. Our estimated slope was 0.41. From our statistical software, the standard error of the slope is 0.15. To get our test statistic, we take the estimated slope divided by its standard error, and that gives us a test statistic of 2.7. There were 400 skeletons in our data set. 400 minus 2 is 398. so our p-value will be calculated from a t-distribution with 398 degrees of freedom. And since we're carrying out a two-sided test, our p-value will be calculated as the probability of observing a value greater than or equal to 2.7 or less than or equal to negative 2.7, which is quite a small probability. From software, it is 0.006. So although our data seems quite noisy, there is still quite strong evidence that our slope is not zero. And we can conclude that there is evidence of a linear relationship between error in age estimation and BMI. In addition to saying that the slope isn't zero, we'd like to have a range of plausible values for what the slope might be. This would give us an idea of how accurate our estimate of the slope is. So we'd like to have a confidence interval for the slope. Here's the formula for the confidence interval for a mean. It follows a general format. It is the estimate of the mean plus or minus a critical value from some appropriate distribution times the standard error of the mean. In regression, a confidence interval for the slope can be constructed using the same format. It is the estimate of the slope, B1, plus or minus a critical value, this time from a t-distribution with n minus 2 degrees of freedom, times the standard error of the slope. Suppose we wanted a 95% confidence interval for the slope for our skeleton example. N is 400 in this example, so we need the value with probability 0.025 in the tails from a t-distribution with 398 degrees of freedom. And using a computer, this value is 1.966. Our estimate of the slope B1 is 0.41, its standard error is 0.15, so our confidence interval is 0.41 plus or minus 1.966 times 0.15, which gives us the range from 0.12 to 0.71. So we're 95% confident that the slope is somewhere in that range. Note that this confidence interval doesn't include zero, so we're again quite confident that there is a linear relationship between error in age estimation and BMI. Let's look at another example, the relationship between average crawling age and temperature. Suppose we'd like to carry out a test of whether the slope is zero for these data. Here are the relevant statistics. Note that the p-value for the test of whether the slope is zero, in this case, is 0.011. So we have moderate evidence that the slope is something other than zero. From the scatter plot, we may have felt more confident that there was a linear relationship here than we were for the very noisy skeleton data. But there are two reasons that lead to the fact that the evidence is less strong for the baby's crawling data. First of all, we had one point that didn't fit the model well. This point contributes a lot to our estimate of the variability of the errors, making it larger and thus making the standard error of the estimated slope larger. And secondly, our sample size is only 12, and we had a much larger sample size for the skeleton example. For both of these reasons, we have less power for the test of the slope for the baby's crawling data, so the evidence isn't as strong. We now have methodology for carrying out inference on the slope of the regression line. And should you want to carry out inference on the intercept, it follows the same pattern. But before we leave this video, we should be careful about how strongly we can state our conclusions. Just because there is a statistically significant relationship between y and x, that doesn't mean that x causes y to change. Do lower temperatures cause babies to take longer to learn to crawl? Or could it be other factors associated with temperature, such as time spent outdoors or maybe type of clothing worn, and that results in the relationship? There are many reasons we may see evidence of a linear relationship between two variables. It is possible, and perhaps what you might expect, that a change in the predictor variable causes a change in the response variable. But it is also possible that it's the opposite. That is, that it's actually the response variable causing the change in the predictor variable. Or maybe the predictor variable contributes to, but is not the only cause of the response variable. Maybe there is a third variable confounding the relationship, or a common cause, or both variables are changing over time. And maybe the relationship is just a coincidence. For example, there's strong evidence of a linear relationship between annual revenue at ski facilities in the U.S. and the number of people who die after becoming tangled in their bed sheets. But this is probably just a coincidence. Often the goal of using linear regression is to answer the question, is there a relationship between our response and predictor variables? And we've seen how we can describe this relationship with a slope and build a confidence interval for a range of possible values the slope might be, and carry out a statistical test for whether the slope is 0, in which case there would be no relationship. Like all inferential procedures, this test and confidence interval require some conditions to hold in order for them to be valid. In this video, we've seen some indication of these conditions. In the next video, we'll look some more at these conditions and how we can check whether it seems reasonable to assume that they hold for our data.